All right, here we're going to look at solving exponential equations that have like bases. And the reason we're going to do this is because it's really going to help us with our next topic when we look at logarithms. So basically what we're basing this off of is that if I have b to the x is equal to b to the y, then I actually know that the exponents x and y are equal. Or to put it another way, let me maybe use some sort of a number here. If I say 4 to something in a mystery box is equal to 4 to some other mystery box, I know that actually if that's true, then the things in the mystery boxes have to actually be the same as one another. There's another way of putting that. So if I take 5 to the x is equal to 25. Now you probably know the answer to that without doing anything fancy. You know that if you put a 2 in for x, 5 squared is 25. But to kind of try to make this look like that, we can say, all right, I'm going to take 25, I'm going to force it to be 5 raised to a power. And of course we know that it's 5 raised to the power of 2, so what that means is that x has to equal 2. If I want to solve something like 6 to the x equals 1 over 216, okay, then I'm going to do the same sort of thing here. Now at first it's going to be a little bit more complicated than the last one because I have 1 over 216. So what I want you to do is at first don't worry about the fact that it's on the bottom of the fraction. Just think to yourself, I'm still going to make this try to match up with the base on the other side. So can I write 216 to a power as 6 to a power? And the answer is yes. If you take 216, you'll get it by going 6 to the 3rd power. Now, of course, we need the bases we're looking at to be on the same level, right, in order to use this principle. But I can do that without too much trouble because I know that that power can become negative, and then that allows it to go to the top of the fraction. And so at this point I know, oh, okay, x must equal -3. So just making the bases match, and that's what's allowing me to make these statements. Now 4 and 8, now I cannot write 8 as 4 to a nice power, but what I can do is I can change them both to be 2. So what I'm going to do is I'm going to say 4 I know is 2 to the 2nd power, and I'll still have the x out there. And of course 8 is 2 to the 3rd power. Then I'll use my exponent rules to say if I have a power raised to a power, that's multiplication. And then once I do have 2 to something equals 2 to something, those two somethings must in fact be the same. And I can solve that little equation that I get. All right, kind of a similar thing happening in example 4. Maybe this would be a great time to pause, try this yourself. All right. But then once you're back here, you'll recognize, okay, I can't write 27 as 9 to a power. However, I can write both of these as 3 to a power. So 9 is 3 squared, so I'll raise that to the x minus 1. And 27 is 3 to the 3rd, so I'll raise that to the x. So just replacing 27 with 3 to the 3rd, replacing 9 with 3 squared. And then be careful here, it's a power raised to a power, so we are multiplying, but we're multiplying by all of that, so make sure you put parentheses around your x minus 1. And so I can go ahead and distribute 3 to the, actually, before I do any distributing, let's just say right now that I know that this and this have to be equal, right? Because we have our bases the same. So 2 times x minus 1 is equal to 3x. 2x minus 2 is 3x. Subtract 2x from both sides, so x equals -2. All right. And just to kind of put in perspective again what's happening here, what we're really saying is that if you take 9 to the negative 2 minus 1, that will equal 27 to the negative 2. Or in other words, 9 to the negative 3 is equal to 27 to the negative 2. Go ahead and check that in your calculator and confirm that that is in fact true.